Right, ladies and gentlemen, now Mark will be coming on very shortly. We're just trying to establish connection with him right now. Now, I'd just like to mention for those of you who are tuning in here and of course online that towards the end of the day, we will have a QR code. We'll have a session in which you can actually share with us your feedback. It's going to be very important for us going forward in the conference as well. So do spend that little bit of time to ensure that you give us your thoughts and your opinions on the conference thus far. Okay, so we're just establishing the connection right now with Mark, where he will be presenting, he'll be introducing this entire session. Just a minute. All right, I've just been advised, ladies and gentlemen, to introduce our first speaker. Just a second right here. Okay. Dr. Jysoo Lee, Dr. Jysoo Lee, Facilities Director of Research Computing KAUST, King Abdullah University of Science and Technology, will be presenting right now. Ladies and gentlemen, do enjoy this.
I am Jysoo Lee, Facilities Director at King Abdullah University of Science and Technology. Today, I want to give an overview of HPC and AI services at KAUST. KAUST is located at the Red Sea. It has a beautiful campus and state-of-the-art facilities. The complex also includes residential and commercial areas. So at KAUST, we call the president of KAUST is more like the mayor of the small town than a university president. Let me start with our computing infrastructure. Shaheen is our flagship system. It has the 5.5 petaflops of limpet performance, powered by about 200,000 Haswell cores. And this is one of the largest all CPU systems in the world. And that's by design. We want a system easy to access and easy to use. And that strategy has paid off. Right now, more than half of the KAUST faculty are using Shaheen. As you can imagine, that is a very unusually large penetration of the computational science activities. Over the time, we have been making improvement both in hardware and software. For example, recently, we have added 37 petabytes of storage on top of the 18 petabyte we already had. But there's no getting around, the system is getting old. So the procurement of its successor, Shaheen 3, is already in progress. And we are targeting to be operational in 2023. Shaheen 3 will be another major investment. And the major departure of the Shaheen 3 is that besides traditional HPC workload, Shaheen 3 will also accommodate AI and hybrid workload too. We also have a system called Ibex. This is a DIY cluster. Basically, my team built from scratch, and roughly 10% of the Shaheen. And you might wonder why we need Ibex when we have a Shaheen. And because there are some of the computing demand, you cannot accommodate by Shaheen, or Shaheen is not the best place to accommodate it. So we find that using both Shaheen and Ibex together is far more efficient way of meeting the computational demand of the campus. Now let's talk about how we are using these wonderful facilities. What I've shown here is the domains of science is popular at KAUST. Overall, I feel that science is being done at KAUST is not dramatically different from that of the shared computing facilities, like the NSF Supercomputing Center or PRAISE centers. Over the lifetime of Shaheen, it has provided more than 6 billion core hours, and it supported about 600 projects from 200 distinct PIs. What I've shown here is a core hours used by domain sciences. And as you can see, we are covering very diverse domains. one aspect we want to pay attention is that are we taking advantage of the capability that Shaheen brings? So what is shown here is the amount of core hours used by how many nodes does the job need. So jobs that need more than 1,024 cores are roughly 60%, 63% of the total usage. And extreme jobs that need more than 16,000 cores are 25% of the whole usage of the core hours. So we are comfortable that we are taking full advantage of the capability that Shaheen brings. Now let's go beyond the numbers and look at the particular examples. So I want to give a couple of examples. The first one is by Professor Ibrahim Hotep. His dream is to build a virtual model of Red Sea. What I mean is that he wants to predict the weather tomorrow, and also he wants to predict the flow circulation of the next winter. And if the oil spill happens, he wants to know how that's spread out. To make that happen, that often he has to do 100 meter resolution simulation. In some cases, 10 meter resolution simulations. And as you can see, that requires huge amount of computing power and storage. And I'm happy to say that KAUST is only a few places in the world that can support this kind of big dream. The second example I want to say is by Professor Hong Yim. He's studying combustion process. So this is the very simple process he's studying. So the fuel is coming from left, hit the boundary, ignite, and the flame front evolve. So this is certainly looks like a textbook example, and he wants to know how the flame front evolve in space and time. Even for this kind of textbook example, the process itself is not fully understood. And also you can see the implication of understanding this fundamental process. If you understand this process, it has a practical application such as like internal combustion engines. And with the KAUST computing facility, he was able to do most accurate simulation ever on that process. And that's how we are supporting our researchers. Shaheen and Ibex are asset of KAUST, of course, but I also feel it's an asset of a kingdom. That's why, besides serving the need of KAUST campus, I'm also trying to help the kingdom too. So right now, I'm providing computing services to 18 organizations in the kingdom that include a dozen universities and a few government agencies and a few industries. So let me give a couple of examples. So with Aramco, we have wonderful collaboration going on. So this is one, in this case, they want to do reservoir simulation, which is a key part of their operation. At that time, they are doing million cell simulations, and they want to enhance their resolution by 1,000,000 times. One of the problems they have is that there is no computing facility they can use to test and validate the code. And that's how KAUST comes in. So KAUST not only provides a computing facility for Shaheen for them for a few days, but also we provide expertise so they can optimize their code. The result is a great success. They are able to do 1 trillion cell simulation. And that was a world record at the time. It is always nice to have a world record, but also it has a practical implications. What is shown in the picture are pockets of oil only visible at the higher resolution. And you can imagine what are the implications of that. So between KAUST and Aramco, we have 2 more world records, and we are maintaining wonderful collaborations there. So this is another example. There is a government agency called KA-CARE, which is responsible for the nuclear and renewable energy. One of their activities is to have an understanding of the solar radiation and weather conditions that impact solar energy production. The problem they have is that their computing facility is not adequate for the goal. So that's how KAUST comes in. So working together, we are able to simulate 15-year data for the weather and atmospheric conditions. And the data is archived in the Solar Atlas. So this Solar Atlas is used to optimize solar energy production. So for example, if you want to decide where to build a solar farm, this kind of atlas can be handy. And we are now working together to provide daily forecast of weather and atmospheric conditions that impact solar radiation on Arabian Peninsula. Another example with the private sector, with the Saudi electricity company. They are the one providing electricity to entire Saudi kingdom. And one problem they have is the loss in distribution. So their loss can be classified in technical loss. This is based on the infrastructure they built for the distribution of electricity. And all other things are classified as non-technical loss. The problem they have is the technical loss is on par with world average, but non-technical loss is significantly higher than world average. And they want to tackle the problem. So my team worked together with the SCC engineers, start with the building a dashboard. That is to display and analyze customer data. And by that analysis, we identify the problem that we want to focus on anomaly detection. So what I mean is that there are sites is consuming far more electricity than the size of the breakers. The way they are using to detect this anomaly is sending people randomly to the site. The problem is the accuracy is only 3%. So you need far more resources to make that happen. So my team worked together with a CC engineer is use machine learning tool to enhance the accuracy to 75%. So that we build this prototype. And if they apply this prototype to the daily operation, they estimate they are going to save $20 million annually by detecting these anomalies. That is kind of what my team bring to the kingdom. So I explained how we are helping the kingdom with the computing resources and expertise. But the problem is that eventually it's a problem of the human capital. So what I mean is that suppose the kingdom has a dream, ambition to move into the digital economy, and you need human capital. For example, you need people that use all these wonderful technologies and solve a problem at the hand. And kingdom has a shortage of these people, like many other countries. So one area we identified is engineering simulations. And one tool we identified, there are tools from Altair and ANSYS or COMSOL that is kind of lower the barriers of expertise that's needed to solve this kind of problems. So we started with ANSYS because of that is the most popular tool in the kingdom in the area of engineering simulation. So we held 7 workshops so far, and we had more than 400 people attended. You might think that number is not large, but this workshop is not lecture style workshop. but it's one-on-one tutorial, hand-on workshop. So number is actually not small. And also we are working together with the ANSYS for the certification programs. And right now, about 200 people have certified through this program. And also we are also trying to address the license issue with ANSYS together to lower the barrier for the entry. And based on the success we had for the ANSYS, we move into MATLAB, which is kind of the easiest way for the engineer to start working on the simulations. One I want to mention is a building community. You need a forum that everyone in the HPC get together and share the information, discuss ideas, and discuss collaborations. Fortunately, there's an event called HPC Saudi that has been going on about 10 years now. So KAUST has been always actively participating in this event. We host the event twice. So what is shown is the event that we hosted in 2017, which is regarded as one of the most successful events. But besides hosting it, we have already participated in this event. That is my story of running HPC and AI operation in the kingdom. Thank you for listening.
Thank you very much, Dr. Jysoo Lee. Moving on, ladies and gentlemen, next we have Professor Sean Smith, Director, National Computational Infrastructure, NCI, the Australian National University, ANU, Australia. Here is Professor Sean Smith.
Hello, everybody. Very good to see you all. And it's a pleasure to provide a presentation today as a refresher and update on activities that we are undertaking at NCI Australia down here in Canberra. So without further ado, I will get started. So NCI, in Australia, we have two Tier 1 supercomputing facilities. We've got NCI is in Canberra, across on the east coast, as you see there with the star. And then, of course, the Pawsey supercomputer facility is across on the west coast in Perth. And you'll hear much more from Mark Stickells, my good colleague in Perth, about Pawsey a little later. And I'm going to give you a highlight today around NCI activities. Both facilities run substantive operations in support of Australia's research sector. We have both broad-ranging support and also somewhat different, if you might say, mission focuses in terms of what we provide. Pawsey is very heavily integrated with the Square Kilometre Array, obviously, the radio astronomy. NCI is very heavily integrated with climate and weather and geoscience areas of activity, aside of the broad spectrum research support that we offer to the community. So, a little bit about how NCI operates. So we are very grateful for funding from the federal government, which underwrites the major part of our large infrastructure upgrades, each new major generation. In addition to that, the operations of NCI have been very much underwritten by heavy commitment and engagement from the foundation collaborator organisations that you see there, and that's the Australian National University, whose lovely campus our data centre is on, and also 3 different government agencies, the CSIRO, Geoscience Australia, and the Bureau of Meteorology. In addition, more recently, the second group of 8 so-called university, UNSW Sydney, has joined as a major collaborator. And then we have a whole swath of engagements with virtually all of the university sector at different levels of engagement, and some industry activities as well, also with independent institutes of one sort or another. And so collectively then, the government has underwritten the large-scale upgrades for us. And in terms of our operational activities, Federal government provides about 25%-ish, and all of those other collaborators and contracting organizations provide the remaining 75%. So it's evolved into a reasonably well-balanced, co-funded kind of operation. Not surprisingly, because we deal with a whole wide swath of different universities, as well as the agencies, NCI facilitates, the spectrum of research from, the outstanding fundamental research groups who are working in their own research disciplines in the university schools, across into what we would call strategic research, which ties to various state and federal priorities, environmental research, medical, geoscience, agriculture materials, venturing across into applied research. The weather forecasting component there is very much a collaborative activity. The day-to-day operational weather forecasting is done by the Bureau of Meteorology on their in-house, dedicated machine. But NCI is very much a collaborative sandpit for the Bureau, as well as CSIRO and university groups who are building new codes and new techniques and new modeling methods, which ultimately then plays out into the operational activities as it matures. We also then have some degree of industry engagement. That is mostly with small to medium-sized enterprises who are kind of spinning up, and a facility like NCI is the best place for them to be able to build their operations and their activities. And I'll mention some examples of that a little later on. So it's a fairly broad spectrum from very fundamental through into relatively applied activities. A few comments here on how NCI enhances Australian research, and I'll just cover a range of different areas. But the wording there, I think, is important. How does it enhance research and research broadly? So, I think we all would be familiar that if you dialed back 15 years-ish or so, the kind of groups who would be using supercomputing facilities such as ours would be heavy-duty modelers, basically. But the power of supercomputing and data services has grown so much that these days it actually underpins virtually all parts of research that are done in the country. And so that has implications for the kinds of communities who are knocking on our door. And I'll talk about that a little more later on. And I gave hints towards that in the abstract for my talk today, that the use paradigms are changing and evolving, and we need to adapt to that. Because it's an underpinning tool for all of research virtually these days, as opposed to just hardcore modelers. Okay, so a little bit on our current large machine, which is named Gardi. Gardi was stood up at the beginning of 2020 in full form. It came in around about 10 petaflops, which landed it at about number 24 on the top 500. Currently, I think it's number 53 as of the SC meeting last year. It was significantly faster than its predecessor and has been a great workhorse for Australian research in this past it's the first 2 years of its journey, shall we say. Around about 3,000 CPU nodes, 48 cores, something like around 150,000 cores all up, and 160 GPU nodes. It's very much a heterogeneous facility and was specifically designed for that purpose. And so the reason I put the two images at the bottom there is that when we designed Gardi, we were specifically not going after the largest petaflop rating we could get. We wanted a machine which could handle a very broad range of workflows, because that's the nature of the research sector that we need to service. And so I think you could think of Gardi more as the Porsche four-wheel drive than the Formula One machine. But it's been a tremendous underwriter for the research sector in Australia over this past couple of years. Running both high throughput computing, but also running some very large runs as well. The largest we did was, I think, just a touch under 100,000 cores, which was an astronomy simulation that was done last year as a part of one of our flagship merit programs. So that's Gardi. A little bit more about, this is in some sense bread and butter for the facilities that you're listening from today, but it is an important factor of what we do. And it's this idea of co-location of the very large high-performance data file systems and the compute engine. And so in the picture here, you see the high-performance Lustre file systems at NCI. We're now tipping over 100 petabytes of high-performance storage in our data center. And it's about 20 feet away from the guarding machine. And so that gives us extremely fast transfer of large amounts of data, which for us has been one of the delineating things, I think, about what NCI tries to deliver for the research sector is that ability to use very large data sets and have them accessible to really heavy grunt analytics workflows that can run on the machine. And more recently, as we've built out our interfacial cloud, which I'll touch on later, we're building platforms so that users can come in onto the cloud and then farm out onto the big machine, run their analytics and pull results back into the cloud in a fairly flexible way that we just couldn't do even a few years ago. So this is a nod to my friend Mark and the Pawsey Supercomputer Center out west, and simply to make the comment that because we have these two tier 1 facilities in Australia, we do work quite hard to tag team between the two facilities. And Pawsey's wonderful new machine, Stonix, is coming up later this year. In part, I think, is up already. And Mark will tell you more about that later. But that staggering effect between the times of which we lift up our machines is quite important, so that the country has access always to a real front-edge machine at any given time. And it's been a good strategy for us over the last decade. And so with these large data sets, this is sort of an example of the sort of things that we need to deal with. And NCI was led down this pathway by precisely those engagements with the large government agencies I mentioned early on, who are amongst our founding collaborator team. Because, for example, Geoscience Australia signs up to the international agreements for the large satellite imaging data sets. And so these come streaming down and get transferred down under to Australia for our part of the globe, Australia, Antarctica, Southeast Asia. And then Geoscience Australia worked with NCI and said, okay, you need to host this because it's not just something that we're going to look after, it's going to be something that the broader community needs access to and want to be able to use. So it sits better on a national facility such as NCI. And that kind of led us down this pathway of, as you see here, looking at the whole issues of rapid ingest of large amounts of data, dealing with the quality assurance, the management, the curation of the data sets so that they follow the fair data principles, and so on and so forth. And so this is done for these different types of data sets that I hinted at, and I think I'll touch on a few of them as we work through the slides here. And so it is very much, as we evolve, it's very much a matter of working as hard as we can as a facility to integrate the different components that are necessary to deliver, ideally, a seamless service for clients who come not just from traditional hardcore HPC, but also from newer communities who have different sorts of use modes. And so you see the kind of topics down below that we need to be addressing in our research. And Jysoo gave some lovely examples of work being done at KAUST in related areas. And these are some of the ones that we've been pulled into heavily in recent years. So now this is one, the whole thing around responsive event, responsive event measurement and tracking has become a big issue and is becoming an even bigger issue as we go forwards. We hit this, obviously, as you know, in the so-called Black Summer a couple of years ago here in Australia, where we had pretty horrendous bushfires. And that, I think it really was a stimulant in Australia, and it moved community opinion, and it also eventually moved government, such that, now we see flow-through funding for comprehensive monitoring and management processes around these sorts of extreme climate events. And right now, we've got the opposite end of the scale that East Australia is under flooding at this point in time. And so, you know, all of these things are things that are going to need to be dealt with and need rapid response and processing and so on. And we all saw what happened with COVID as well. I think that might actually be my next slide. So yes, indeed it is. So this was another, you know, rapid response thing that we had to respond to. And I know our other facilities also were doing the same thing. But because we had new capacity on Gardi, we were able to do some really large awards of time for exploring new potential drugs and therapies for things like COVID. And that will continue to be an active area where we push resources going forwards. The other component of climate and weather modeling that we're engaged with is not so much necessarily the rapid response kind of thing that I highlighted a couple of slides ago, but it's the systematic and progressive build out and enhancement of the climate and weather community's ability to predict. And so this is a multinational, multi-generational program is building the major codes which are able to simulate global climate and weather patterns with increasing accuracy and decreasing grain size as we go forwards. And in fact, it's one of the poster childs pushing the sector towards exascale compute, because the implications of being able to do these kinds of simulations, you know, reaching down to sub 10 kilometer grid size across the globe are enormous and will enable unprecedented levels of risk mitigation, I should say, in this area. And so with all of that code development goes enormous model data sets. And so this CMIP6 you see is the coupled model intercomparison project. And these are enormous data sets which are generated by the major simulation codes for the purpose as a benchmark for the community to be able to keep developing its capabilities. And we host these data sets down under because, of course, they're used by many different parts of the research sector. So that's another exemplar. This is one of our engagements with well, I say small to medium industry, but DHI actually is not so small these days. It's a company which does high performance simulations of large bodies moving in constrained water channels, essentially. And so DHI is becoming more and more, becoming larger and larger in their activities. They've been a co-worker with NCI here in Australia, and I think also with Pawsey now for several years. And it's been a really successful program. And the kind of thing they do, for example, is they can model how ships can move in constrained channels with ports, which has an enormous impact on how much dredging you've got to do, how deep your channels have to be. And the Port of Brisbane, for example, here in Australia is one that doesn't have a beautiful big harbour like Sydney does. Sydney's got two of them. Brisbane just has essentially an estuary and a river. And so dredging is a big deal for them. And DHI did huge service for the port in terms of helping them understand what they needed to do, how much they had to dig, and so forth. Genomics is becoming also a really big deal, obviously, because it has tended to be a research domain, but it's moving now and transitioning into a clinical medical activity, which means that the sheer volume of genomic sequencing is going to explode in the coming years. And certainly our sector in Australia is figuring out how to make all this work and how to make it work in such a way that what will be really, really large population genomic data sets can actually be made available for the research community in order to bootstrap the enhancements of the science itself, which ultimately feed back to improved clinical medicine. And so it's one of those kind of virtuous cycles, but it doesn't work if you can't find a way to robustly and reliably consolidate these really large genomic data sets. And you can imagine there's all kinds of legal issues around all of that, which need to be explored. and technical issues as well. But we are very proud that we've just released it's called the MGRB, the Medical Genomic Reference Bank, and that last little dot point. Just yesterday, the announcement went out that that's been now curated up to national dataset standards and released. It comes from the Garvan Institute, and it's the first of its kind to be made available in that way here in Australia. So I want to scoot on a little bit because time is running by. This is just a really quick pie chart showing the different allocation of Gaadi's capacity across different organizations. And you see universities are big. The big agencies are also big, obviously. But I'll scoot past that and just start to look at some of the evolutions which I said I would talk about. You know, the sector is moving, and we've got, for example, genomics. You know, the usage paradigms of groups who want access to what are mostly cloud-based tools, but sometimes need serious HPC as well to reprocess the genomics data sets. Their usage profiles are completely different from the traditional, you know, for example, large-scale CFD sorts of workflows. They run hot and cold. They need user-friendly cloud-based tools to work from. And it's a very different kind of paradigm, and it's something that our facilities are working to adjust and adapt to provide those things. And so data is becoming centric and enormous and central to the sorts of services we can provide to the sector, coupled tightly with the compute and the storage, obviously, and the networks. And so that kind of integration of all these facets is something that we need to work and are working really, really hard on. And as I said, this is summarizing in a sense what I've described, that it's being driven by new use communities coming online, and not even just the new ones, even the communities like climate and weather, who they know how to do batch Q HPC, but they want to have analytics driven off the cloud because it's just so much easier for them to do their post work. And so it's an integrated environment where NCI has to couple these things in-house, but we've also then got to work on interoperability with other parts of our sector, our major collaborators, the international facilities, Pawsey across out west, commercial cloud, obviously, and other research infrastructures here in Australia. And it's that integration which is really a key evolution point and driver for what we're doing currently. And I think that leads me to not quite the end, actually. We also are introducing more flexible merit schemes. We used to do a once-a-year call. We still do that for the heavy-duty compute groups, but we're now introducing a quarterly call for flexible access to combinations of cloud, HPC, and data storage to help onboard these newer user communities. And the cloud itself, we've been working really hard on over the past 2 years. Our new cloud, Niren, is now up and operational. We use Open On Demand as a platform to allow users to come in and access their favorite tools and farm out as need be onto the big compute engine, and then bring the results back and analyze them. Okay, so that's my time, and I think we have discussion with forum later on, so no questions now, but thank you very much.
Thank you kindly, Prof. Smith. Thank you very much. And now, ladies and gentlemen, I'd like to introduce our next speaker. This is an in-person speaker right here in Singapore, in Suntec City. We have Associate Professor Tan Tin Wee. He is, of course, the Chief Executive, National Supercomputing Center, NSCC, Singapore. Here is Prof. Tan.
Thank you very much. Thank you very much for that kind introduction. My name is Tin Wee, and I'm the Chief Executive of the National Supercomputing Center, and I'll be here to give you a few updates up here from Singapore, what we've been up to in the last 12 months or so during the COVID period. Thank you very much. Next slide, please. Thank you. We are the national supercomputing infrastructure that the National Research Foundation of Singapore has funded in order to provide Singapore's petascale computing resources, a national high-performance computing resource to make available to all our universities, our research institutions, and our government agencies, and in particular industries, not just large enterprises, but also small and medium enterprises. Now, we are in Singapore, where the population is kind of small, and our land space is even smaller. And in Singapore, our research community is also pretty small by all standards of comparison. However, we are trying to punch above our weight by ensuring that as many users as possible get on board on the advantages of using high-performance computing. And we are truly aligned towards our Singapore's key research thrusts of in our National Research Foundation's research infrastructure, RIE 2020 and 2025 research plans. And this infrastructure will support all researchers in these different trusts to leverage on high-performance computing, high-performance storage, high-throughput computing in order to gain the competitive advantage in research. Now, there have been several upgrades to our Aspire 1 supercomputer, and I'll be here to explain to you what our future directions might be. Now, just a quick recap. The Advanced Supercomputer for Petascale Innovation, Research and Enterprise, Aspire, was launched in December 2016. So we've sort of been running this system for the last 6 years, and we need to move on to greener pastures as the technology has moved on significantly. At that time, our Aspire 1 system comprised a 1.01 petaflop system with these specifications which I've shown on screen. Over time, we've had to add on a Cray XC supercomputer facility to support our weather and climate modeling research community. In addition, in the gap running up to our second supercomputer, we have added on a high throughput system as well as 6 DGX1s for our AI platform. And we've considerably upgraded our NSCC data center in order to operate at a far more efficiency that will allow us to stretch our dollar to the maximum. Now, Aspire 1 is located at quite an unusual location, and it's at level 17 of a high-rise a block of building at Fusionopolis, above in a MRT station. That's our mass rapid transit subway. And so whilst it provides a convenient location for many of our researchers, unfortunately, at that high level of locale, it poses some degree of challenge, as you well can understand and appreciate. First of all, 1 megawatt of power has to be brought all the way up level 17, and the bus bar that goes up is something about the size of the trunk of my tie, you know. And that high-rise space is about 400 square meters, and we make use of the fact that we are at this high level above ground, making use of the high winds up there to expel the heat of our data center. And the hot aisle of our data center is running something like 40 degrees on a regular basis. And we're able to throw out the heat to the upper atmosphere without causing land and livability problems if we were to expel the heat at the ground level. Our data center hall lives at this high location due to various reasons that I shall not belabor the point on. But we make use of warm water cooling because the temperature throughout Singapore's weather spans between 25 degrees in a cool 4 a.m. in the morning, right up to as high as 35 degrees during the day. But still, if our warm water that we use to extract heat from our hot cooled chips can expel heat at 45 degrees, there is a sufficient temperature delta in order to provide that heat gradient to allow the heat to be extracted to the atmosphere. So we are able to operate at a PUE of something like 1.36 initially, but by ensuring that we have all these 3 different integrated cooling mechanisms, we were able to, with the help of some big data analytics that we put in place, to reduce our PUE down to as low as 1.08, which is pretty good for a tropical data center, sitting right on top of the equator. This combination of 3 integrated cooling systems comprising a warm water direct-to-chip cooling system, 40 degrees in and 45 degrees out, to combine with a rear door heat exchanger tapping on the chilled air conditioning cooling system of our office block. And with minimum air conditioning cooling, we are able to achieve that level of efficiency, 1.08 on a good day. And we have added on a hot aisle and cold aisle insulation to ensure that the system operates at even a more efficient manner. So this direct-to-chip cooling is a pretty regular technology by today, but 6 years ago, it was something that was pretty new to us. So today, it's pretty commonplace, and we are happy that we actually bet on the right horse, so to speak. Direct-to-chip cooling is now pretty commonplace. And for us, at that time, it was something that was challenging to achieve. So in the next slide, I'll talk about how we were able to make use of the fact that we are at the upper floor at 17 to make use of dry coolers. So in other words, the evaporative loss is actually 0. This is a closed loop, and in Singapore, you may know that we have a limitation of using water, fresh water, and as a result, evaporative cooling for us is it is not quite a good idea because of the very high cost of fresh water. And therefore, by using a closed loop and from a dry cooler system, we were able to expel the heat at the level 18 floor, which has pretty high winds up there. So we make use of the Smart Network Operations Center, an NOC that has 24/7 monitoring the data center health in terms of the CPU utilization to power consumption, relative humidity, temperature, chilled water, and so forth. But our integrated data center information management system, DCIM, and the building management system provides a good integration of sensor systems. We have something like 6,540 sensors, right? So this is all integrated and data collected for us to analyze how we can further improve the day-to-day operations of our system. Going forward, the next generation of supercomputers that we will bring in includes the following architecture. We call it Aspire 2A for one of the better operational terminology. This means that in our second phase of our funding, we will be bringing Aspire second generation supercomputers in 2 phases, phase A and phase B. For phase A, we're due to install this system sometime by the middle of this year, an HPE Cray XE, and we're going to go right up to something like 98,000 cores and 352 A100 latest generation GPUs. We're going to add in a few high-frequency nodes, as we have a number of researchers that require this, have this requirement, plus high memory nodes. Some of these high memory nodes and the high-frequency nodes will be carved out for us to support a quantum simulator system that we, in collaboration with the Center for Quantum Technology in Singapore, provide quantum compute capability to our ever-growing research community in the quantum computing space. So we will have 10 petabytes scratch and 45 petabytes of storage, and we will use a hierarchical storage management system and backup remotely on another campus, the Nanyang Technological University campus. So this Aspire 2A system will be based out at the National University of Singapore Innovation 4.0 building. This building will be the new home of our next supercomputer, and it was completed in the 4th quarter of 2021 last year, in the midst of the pandemic. So it's co-located with the I4.0 tenants, which include the headquarters of the AI Singapore, the Artificial Intelligence National Initiative of Singapore. So we're in close proximity with our colleagues in the AI community, such that a large part of our data center, well, almost nearly half of the data center itself at the I4.0 building, which is something like level 2, much more decent location as compared to level 17 in our Aspire 1, we are able to interact with our AI experts in order to help us design and operate a much more efficient data center, certainly much more efficient than we hope for Aspire 1. There are several power-saving mechanisms, including a unique feature. Our Cray-XC will be operating in a data center hall that does not have any air conditioning. We are sucking in ambient temperature, which, as I said earlier, ranges from 25 degrees right across to 35 on a hot day, without any air conditioning, but just with a dehumidification system. And this dehumidification system will extract the water vapor that's in our humidity is something like, can go all the way up to 100%. So this unique feature is something which we hope that will work well for us and cut down the electricity consumption as well. So this unique data center design is specific for our tropics to demonstrate to the data center community, the IT community, that our system of using the dry cooler system can work, and we've pushed the limit without air conditioning. We'll be leveraging on Singapore technology also to add on to a new feature of our rear door heat exchange system, which we have been using in our Aspire 1 system, using the so-called CoolLogic's thermal siphon gas system that was actually designed in Aspire 1 supercomputer by our colleagues from Institute for High Performance Computing, working together with the vendor CoolLogic's. We have made it a point to create digital twins of this data center and supercomputers that will occupy this data center. And it will allow us to create what-if scenarios as well, in addition on top of the intelligent monitoring system, which we have been familiar with in Aspire 1. In all, we hope that this data center will be as environmentally sustainable as possible. In fact, we started off with managed to attain the Singapore Building Construction Authority's Green Mark Platinum Award in 2021. So we hope to move on to even greater heights of achievement in ensuring that this data center in the tropics will be operating as low a PUE standard as possible. One other feature of this I4.0 building is our proximity to two research organizations, and that is the Singapore Synchrotron Light Source, SSLS, and next door to our I4.0 building, will be about 100 meters away, is our marine wave basin for the Center for Offshore and Marine Sciences. And they have a huge, something like a 15-story deep a swimming pool where it's filled with water, and they make use of this marine wave basin, one of maybe something like half a dozen in this world, to do offshore and marine modeling and simulation of marine structures, ship hulls, and mimicking harsh weather conditions in order to improve the design of our maritime sector, shipping ships, right? Okay. Now, our 4.0 building will have two components of Area A and Area B, and the Area A will be the one where the Cray-EX supercomputer will be located, no air conditioning. Can you imagine a data center in the tropics with no air conditioning? Area B will be home for our CoolLogic's rear door heat cooling system, and this thermal siphon system is making use of a rear door heat exchange system, as described here in this slide, right? And it makes use of a refrigerant that will be extracting heat from our Area B supercomputers in such a way as they will evaporate the the refrigerant, and which be collected and circulated through through a condensation system, and this will pull out the heat from the rear door heat exchange system of these supercomputer racks. And this was designed on our Spire-1 supercomputer by colleagues from HPC, as I mentioned earlier. The HP Cray EX system will comprise 4 racks. One of them has been delivered, and 3 more are currently being shipped at this point as we speak. Now, the NSCC Phase 2 will therefore eventually include a data center resilience strategy. Would mean that Spire-1 will be concurrently operating with the Spire-2A system, Spire-1 in the Fusion Police high-rise, and Spire-2 will be in NUS 4.0 data center building. And all this will be backed up from NTU, the Nanyang Technological University, BCP, Business Continuity Disaster Recovery Site. So our possible DC roadmap technologies will comprise this this progression of us moving from conventional data centers prior to 2015 to a high-rise hot data center, moving on to a hot data center in I-4.0 building using digital twin technology. But going forward, we are looking forward to a new project that we are launching with the Singapore Liquefied Natural Gas Consortium, which is based out in an island offshore of Singapore. And that is the site of an LNG receiving terminal. And those of us who know about LNG know that the liquefied natural gas is something like a minus 162 degrees centigrade. And this represents a lot of cold energy that we could tap on in the form of industrial symbiosis. So this data center that we hope, a little data center experiment that we hope to construct on the premises of an LNG receiving terminal will be one of our projects that we hope to have collaboration with SLNG to pioneer new cooling opportunities in a method called industrial symbiosis. To tap the waste cold energy of a large industry like LNG regasification, and couple that with our data center operations. Going forward, we hope that by 2025 we will have a floating data center combined with the photovoltaic solar farm on one of our reservoirs or in the sea offshore of Singapore. And beyond that, we hope, currently negotiating with colleagues in Finland about potentially locating our future supercomputers in enjoying free cooling in an Arctic location, and tapping on hydroelectric power. So this issue of maintaining and sustaining data centers that house hot supercomputers is something that we are pretty concerned of, and is part of our commitment to sustainable goals of environmental friendliness and green, using renewable energy from sources with low or zero carbon footprint. So this gives you a snapshot of how our work supports HPC in Singapore and across the world. And this effort of building green data centers represents our responsibility towards the environment in order to support our research in a green and sustainable manner. So we managed to get hold of a number of research users as listed here in this slide. Our environmental agencies, meteorological surveys, our Center for Climate Research, as well as the Singapore ETH Center carrying out research in the cooling Singapore, as well as our Precision Medicine Research Community, or PRECISE, which connects our clinicians together with the genome scientists. We have just recently, a few hours ago, signed an MOU with the Singapore's premier hospital chain called SingHealth, and in order to deliver an edge supercomputer to our healthcare personnel. Together with another edge supercomputer, which we launched a few months ago with the National University Health System within the university education framework. So these HPC activities will democratize access to HPC to encourage increased usage. One of the things that we are launching is a supercomputing digital sandbox that will allow a smooth and seamless access of supercomputers to our end users who may not be HPC experts. Moving forward rapidly, our effort to deliver transformational solutions for Singapore through HPC provides that degree of innovation challenge, especially for the environment, to encourage local teams in our construction and buildings sector, as well as our geospatial communities, to improve the way they make use of high-performance computing to herald an era of smart nation, high-performance computing and AI facilities that translates into societal transformation for smart nations initiatives. Our international collaboration through annual call for projects to the Fugaku system, thanks to our colleagues in Japan, notably RIKEN-CCS and the Research Organization for Information Science and Technology, RIST of Japan. They've kindly donated 1 million node hours to our researchers to enjoy the benefit of accessing the currently ranked world's fastest supercomputer, the Fugaku. About 5 projects have been awarded as listed here, and you can see they span a wide range of research communities and that will benefit from access to the world's fastest. So even though Singapore is only at the 1+ petaflop range and eventually to something like 8 to 10 petaflops aggregate in Singapore, you will see that already our researchers, through the friendship that we have constructed with and nurtured with friends from outside Singapore, especially notably our Japanese colleagues, that our researchers will have access to run their supercomputing projects on the world's fastest. We also have partnerships and collaborations with international groups as well as local groups in order to explore green and novel DC architectures, as I mentioned earlier, with the Singapore SLNG. We also spend effort to nurture talent in building a strong manpower base in order to promote better utilization of HPC services that we are offering on our platforms, Aspire 1 and Aspire 2. Annually, we run in collaboration with the HPC AI Consortium, HPC AI Advisory Council, to run the APAC HPC AI competition that encourages international teams in the APAC region to showcase their HPC and AI expertise through competition. And this is a very strong and powerful effect that we have on our young people to seriously consider HPC as one of their career options going forward as they graduate from our tertiary educational institutions. So cross-border activities also include MOUs with Finland and Australia. As I mentioned, our roadmap includes the possibility of putting our future supercomputers in extremely green environments, data center friendly locations, such as in Finland, as well as in Australia. Certainly, a large part of our supercomputing resources are negotiated with colleagues in Australia, and we're really grateful for them helping us and bailing us out as our current demand exceeds what we can offer at this point of time. So it's this kind of cooperative environment that we hope to build such that the feast and famine cycles that we in the HPC service provider community experience on a regular basis. When we get the grant, we buy a huge computer, and we are in a feast situation where the supercomputer may be perhaps 50% utilized. What happens to the other 50%? If we can create a model to share the computational resources with others who are in the famine cycle. So right now, our Aspire 1 system, pending the arrival of the Aspire 2 system, we are more or less in so-called a famine situation. So those countries that have supercomputers in a feast cycle can then now lend us some of the supercomputing power, such that sometime in the future, when we are in the feast cycle, we can return that favor back to that kind donor. So this kind of cooperation is something that we're trying to promote, and we hope that through the leadership of our colleagues in Australia, under the able chairman and sterling chairmanship of Sean Smith, that he could lead us to even greener pastures, whereby feast and famine cycles would be so-called, the ups and downs would be flattened. And this gives new dimension to the idea of flattening the curve, so to speak. So in supporting international HPC talent development, we have all kinds of competitions, as I mentioned earlier, and our students take part in other people's competitions. So we run competitions ourselves, and we also encourage our researchers and our students to take part in other people's competitions. And I'm glad to inform you that even though we have such a short history of expertise in petascale computing, our students are already able to reach to the lofty level of being ranked 4th in the world in terms of student cluster competitions. So NTU, well done to all of you students in Nanyang Technological University. So we also run competitions like Data Mover Challenge, DMC, and I think later on this week we will be giving awards for winners of this DMC Grand Challenge, whereby the data movement of research data sets is one of the key things challenges that we're trying to encourage researchers to in the HPC space to pay attention to, in addition to big iron compute resources. So data movement is extremely important. Make sure that the high performance computers are easily able to access large data sets. So with that, I'd like to thank you. This is just a quick update of what we have in Singapore. And moving forward, we look forward to more cooperations with our colleagues worldwide, because we, as in tiny Singapore, are latecomers to the game. And certainly our capabilities and capacities are seriously limited. And yet we want our researchers to really be able to compete with the world's best. By tapping on possibly a globally shared computing resource that can extend from HPC to high throughput computing, HTC, to AI platforms, and beyond that to quantum computing. So may I end that without stealing the thunder from our quantum computing colleagues in Singapore, that NSCC has recently been designated as the National Quantum Computing Facility. And we hope going forward in the future to be able to report to all of you our developments going forward in terms of quantum computing as the next frontier of high performance computing. More about that soon. And thank you very much for your attention.
Associate Professor Tan, we thank you, sir. And now, ladies and gentlemen, an update from down under Pawsey Supercomputing Research Centre. We have its Executive Director, Pawsey Supercomputing Centre Australia, Mr. Mark Stickells. Mr. Mark Stickells, please.
Present at Supercomputing Asia. So in the language of the Western Australia's First Nations people and from the traditional owners of the land upon which Pawsey operates, I'd like to acknowledge country. To the Whadjuk Noongar people as the traditional custodians of the land here in Western Australia, in Perth. You might notice on this slide there's from the Wajiri Yamaji senior artist Margaret Whitehurst, and that's a connection to kilometres north of Perth in the land upon which the square kilometre array is going. From the keynote presentation from Dr. Pierce, that Pawsey is part of an important global super science project, and we've got a deep connection to that. Pawsey itself is named after a pioneering radio astronomer, and this reflects an important part of our focus as a national facility. Just moving. we're one of two national tier 1 facilities here in Australia. We're headquartered in Perth, and we are more than the SKA in terms of our support. We do support the entire national research system, and we manage our facility through the National Science Agency, CSIRO, and a joint venture of universities here in Western Australia, and have been operating as a joint venture for almost 2 decades. We have a long-standing partnership with our partners, and we're currently managing a $70 million major upgrade. I think it's been a very challenging time over the last couple of years, and I think I reflected that when I provided an update last year to this esteemed forum. But I think our wonderful team's risen to the challenge. That's a picture just to share with you. That's a picture of the artist, Margaret Whitehurst. So her art is actually on both of our systems, on Magnus, the flagship system that's currently operating, and Setonix, the new system. Setonix is named after WA's iconic quokka. So I think I might have done this last year, but I do have a quokka to keep me company on my desk here. So this is about life size. It's a native to an island just off Perth called Wodgemup, or Rottnest Island, and we've named our system after this iconic West Australian and Australian marsupial. As Professor Smith kindly acknowledged, Setonix will be a step change in Australian supercomputing architecture. We have phase 1 on the floor now, and we'll begin the installation and commissioning of phase 2 later this year. It's going to be a 50 petaflop HPE Cray EX system with a 30 times increase in our current capacity. Really importantly, and I think it's been a bit of a theme in all the presentations so far, it will be a step change improvement in energy performance, 10 times more efficient than our current architectures. And as my colleague from Canberra observed, it's part of a staged upgrade of national HPC infrastructure here in Australia. It was delightful to have Margaret visit us last year, and you can see we've actually got her to sign the cabinet. It's not in that photo, but we actually have an artist sign her cabinet. I'm not sure how many of centres around the world have had that privilege, but it might be starting something new. So in this picture, I've given you a schematic, a very colourful schematic of the architecture at Pawsey this year. It's gone through quite a significant transformation over the last 3 years. The $70 million program that we've had to upgrade Pawsey is more than just an upgrade of Setonix. It's a 4-year program of over a dozen different procurements over the last 3 years. That's included a GPU development cluster, an upgrade of our cloud infrastructure, a major upgrade of our storage infrastructure to the point we'll have almost 300 petabytes of storage in different forms under management at Pawsey. It's an upgrade to our firewall and network infrastructure, and essentially important commitment to enable us to safely and securely manage data movement at scale. We've also improved our building operations, managing some additional energy demands from this new infrastructure. And we've installed a new visualization facility and cluster called Nebula, which you can see in that screen. It really has been a challenging process over the last couple of years, and we're not through this yet, but project over the last 3 years. A particular commendation to our project manager, Stacey Tyson, and our CTO, Ugo Veretto, who leads a great team of experts. But there's also a range of colleagues, dozens of colleagues, in fact, who've helped in procurement of facilities and communications just over the last couple of years, sharing some just with my peer directors through this session, and I look forward to reflecting on that in the panel discussion. Look, the fact that we're currently running our current flagship systems, and while it's actually a scheduled maintenance day, we're continuing to run hundreds of projects, absolute workhorse systems in Magnus, and continuing to support the operations of square kilometre array Pathfinder projects in What's next on. So as I bring this up, there are several projects that are important to Pawsey this year. We're undergoing a full review Pawsey and its infrastructure, which when it was commissioned and constructed over ago, properties, solar panels, and a novel geothermal solution. But there are technology and others that we're looking to all the potential of that for Pawsey. We are under power support for our facility, and we're doing that in partnership with IRO. I'm just so I'm not a couple of things if that's helping. Just to share, I'll just pause for a moment. Okay, I'll keep going and then see how we go. That's fine. So you don't need to see me, you can just see the CSIRO. We also are undertaking, okay, here we go. So I've stopped the camera as well. So thank you for the audience for bearing with us as we work through this. Okay, so we're undertaking a review of our groundwater cooling system, which, as mentioned in the keynote this morning, has saved well over 40 million litres of water that's vital for us here in Perth as we use groundwater for human consumption. We're undertaking an environmental study of the aquifer just to manage the quality of the aquifer after almost a decade of use. And we're also undertaking a vibration and EMF monitoring and assessment project of our data centre ahead of us installing some quantum computing hardware in the coming months. And just if I can move to the next slide. Importantly, the effort to increase the capacity of the national research supercomputing capability in Pawsey through our move to a pre-exascale architecture has required us to make a significant investment in supporting the research community across a range of disciplines here in Australia. So we've undertaken a strategic 3-year program that provides early access to the systems and architecture for Pawsey, and running a program of projects nationally and internationally that involve us co-funding key postdoctoral and PhD roles, plus dedicating Pawsey expertise to work with researchers. We have 18 institutions involved, over 60 researchers, and have some national and international collaborations in support. We've been really pleased to share our learning and our experience through this program, and we had a conference in late December last year that was very well attended and is aiming to really uplift the national research community to take advantage of our new system and our new architecture. The areas of research that we're supporting include materials science, nanomaterials, engineering, molecular physics, of course radio astronomy, geoscience, virology, and particle physics. So a range of projects and computationally intensive disciplines that we're supporting. The project itself, PACER, has provided researchers with an opportunity to optimise their algorithms, codes and workflows for the next generation supercomputers. And the strategy here is to sustainably scale our national research capability to take advantage of the new supercomputer and create a direct pathway to achieve superior scale on our next generation system. Some of those projects are also done in collaboration with some of the leading users on the national system at Canberra in Gaddy. And so it's providing that staging for further scaling. I think a theme in some of the presentations this afternoon, I'm sorry, is also about skills and supporting the next generation of talent in our wonderful industry. Pawsey's had a very successful track record in working with interns, and we've just completed a 10-week paid program of interns. We had 47 interns working across summer with institutions from around the country, some with industry partnerships, some with a more research-intensive project from undergraduate through to master's level. And they've been using technologies supported by Pawsey and undertaking real projects in science, technology, and/or computing. It's been a very successful program for us. We've more than doubled the number of interns from previous year because we moved to a co-funded model. So the willingness of our research partners to co-invest in this has been demonstrated by the growth in this program. The feedback's been very positive, that we've had a lot of good feedback from the students that have been involved, the interns, and we've had very positive reports of how it's built their HPC and data science skills. We've also had feedback that actually industry recruiters were attending the intern showcase when we held that a few weeks ago, trying to secure some of the talent straight into jobs. So very positive experience. A couple of other things I'd like to highlight. We've been very, in our sort of turn to embrace online and remote training and delivery models, we've launched a Learn at Pawsey platform, and we also supported the launch of DRESA, the Digital Research Skills Australasia platform. So there's a national platform for sharing training and development activities supporting digital research skills. And we've done that in partnership with other key providers in the national HPC and data intensive infrastructure and training support organisations. So a really important message there in terms of investing in our future and meeting the demand for skilled people in this area. My next point is perhaps something I'm taking a little bit of a shine away from the spotlight in Singapore on quantum and quantum innovation, but we are also doing some of this here in Perth and in Australia. It's a really exciting development in our investment in a partnership with a leading Australian startup called Quantum Brilliance. The establishment almost 2 years ago of a quantum supercomputing innovation hub here at Pawsey has drawn national and international attention, and we've continued to scale this development in partnership with Quantum Brilliance. Quantum Brilliance has secured, I think, almost $50 million worth of early venture investment as it goes to demonstrate its room temperature synthetic diamond technology, and plans to install an accelerator at Pawsey in April-May period. So we'll be testing quantum accelerators integrated with classical supercomputing in April-May this year. And that was part of the reason we did the environmental study. It also builds on the back of a pioneer project program that we've undertaken with both industry and research organisations, in which we're trying to demonstrate quantum advantage. So some of those have worked in defence, in machine learning, in logistics optimisation, and in a research sense, the applications around finance and also in education and computer science. More recently, we've invested in a partnership locally with the University of Western Australia, in which we've installed two operating educational quantum computers totaling 5 qubits. We think it's the first of their kind anywhere in Australia, but they're operating with a partnership here with the University of Western Australia. So this area of quantum and supercomputing working together and unlocking another potential advance in the area of computational science and breakthrough for researchers is something we're very excited about here in Pawsey. Now I've gone through this with a few minutes to spare. I wasn't sure whether I was going to have a couple of minutes for questions, but I will make some points here in my closing slide. It's a tremendous opportunity to update you on the activities here at Pawsey and to acknowledge the contributions and collaboration that exist across the various centre directors. What I would like to close on is something that Dr. Sarah Pearce closed on this morning as well, and that was the value of diversity and exploring the range of partnerships and opportunities that we can to enrich our centres. This year at Supercomputing Asia, we've also, as a proud contributor to the organising committee, we've supported the inaugural Diversity and Inclusion stream, which is on Wednesday at 1 p.m. So absolutely encourage your participation or contribution to that scheme. I'd also like to shout out to our interns who have been a wonderful cohort this year. We did have almost a third of our interns and intern project leaders were women scientists and researchers, and we're very pleased to encourage that diversity in our workforce. You also see, I did visit Rottnest Island a couple of weeks ago. We can't get out of, the borders are still a little constrained here in Perth, but we're about to open up to the rest of the world later this week, but I was able to visit Rottnest Island a couple of weeks ago and get what's considered a classic tourist photo, is sitting alongside a quokka and getting a selfie with Pawsey's little quokka alongside for scale. So that's my closing point. I do thank you again for this opportunity to present. I haven't seen any questions from the floor, but I think we're saving those for the panel discussion. But thank you very much.
Thank you very much, Mark. And indeed, we'd just like to apologize, ladies and gentlemen, for the intermittent transmission that we had in the earlier part of Mark's presentation. But as he correctly mentioned, he will be in the panel discussion a little later. So, of course, should you have missed any integral parts in his delivery, please feel free to raise your queries, your thoughts during the panel discussion towards the end of this program right here. Up next, ladies and gentlemen, I'd like to introduce Director, RIKEN Center for Computational Science, R-CCS Japan, and he, of course, is Professor Satoshi Matsuoka.
Thank you. And by the way, to make a minor correction, it's RIKEN, not RIKEN. Okay. Sorry about that. Okay, so I'm Satoshi, and again, it's a very much a pleasure and honor to be here to present. And I'd like to present you some of the details of the Fugaku supercomputer and what it's doing right now. Okay. I have a video, hopefully it will play. Before I start, I'd like to pay a little tribute to the two friends who have unfortunately passed away very recently. One is Hiroshi Nakashima, who was a very good friend and colleague of mine, Kyoto University. I worked with him on many projects, which led to Fugaku. Also, Puchong, who also unfortunately passed away, could not see his long-time dream of Thailand facilitating a world-class supercomputer finally come to fruition, although he was one of the main forces along with people like Joe. Again, I feel very deeply, but of course we have to move on with our thoughts. So Fugaku, if you do not know what the name means, it's Mount Fuji as a symbol. It's a symbol of Japan. It's a symbol of this supercomputer. And the reason it's named Fugaku is that the past supercomputers in Japan have been aimed at facilitating very narrow sets of users, although they have demonstrated world-leading performance like the Earth simulator. But the modern days and age of IT ecosystem with the cloud and so forth, it has to be or edge to cloud and so forth, and AI and everything. The supercomputer has to be very broad in terms of utility, applicability, capacity, user base, applications, et cetera, et cetera, et cetera. So this extreme high performance and also this very broad base would be, the simultaneously satisfying these two properties is idealism for the supercomputers to play a significant part in the SDG goals, or Society 5.0 in Japanese context. And Fugaku was designed to satisfy both. Of course, it's always easier said than done. Of course, it is extremely easier said than done. As we know, if you take, if I paraphrase this to be, let's say, a car, it's possible to build a very comfy limousine. It's very, which may be slow, but it can seat many people and it's very comfortable. Or you can build a racing car, which can only seat one person, but not very comfortable, can be only driven by experts. Driving something that's comfy, useful, and also very fast in terms of automobiles is really hard. And it's the same with supercomputers. So we took on the challenge with extreme parameters, design parameters we had to satisfy. At the time, it seemed when we started the project back in 2010, and eventually set the parameters, it was just deemed like it was seemingly impossible, numbers to satisfy. But so basically, we went to the whole national level co-design process, and we achieved this moonshot-like goal. in 10-year span. So the resulting processor FX, as if you have seen Skorko-san's presentation early on, you'll find that on his particular extremely modern CFD code compared to Xeon, let's say Xeon processor on a per chip basis, not just a node basis, because those Xeon systems have 2 chips on the node and thus use more than twice the power. On a chip-to-chip basis, A2FX would be about 2 to 3 times faster and or 3 times more power efficient. But it's a general purpose ARM processor, so it runs anything that ARM would run the same code as your, let's say, your MacBook or your smartphone. And we employ 160,000 of this in Fugaku. And so the resulting performance is exascale. By some definition. It's not exaflop in impact, but it's exascale performance in real applications. And so put Fugaku in context, with this, let's say comparing to the same, to a cell phone, which runs the same code, basically same program. It's equivalent to about 20 million smartphones, which is by and large about the number of cell phones sold in Japan for the entire year. So that means if you had one Fugaku, if you had a few Fugakus, that'll satisfy the entire IT needs of Japan. So, or put another way, Fugaku constitutes a significant percentage of the entire computing capability of Japan, not just supercomputers, but including clouds and everything. Okay, so that's how powerful Fugaku is. Okay, so here's a little video. I don't know if the video will play. Let's see if it plays. No, it plays. I don't know if we can get the audio. Okay, so if we don't get the audio, I'll just dub it myself. So this Fugaku, I'm standing in this room, and I'm explaining its same name as Mount Fuji. You see the Fugaku logo up on the panel, and you'll see, it's a very large room. So as you'll see in the video, it occupies about 3,000. The machine occupies about 3,000 square meters, about 50 meters by 60 square meters. Well, and the room is, of course, bigger. So it's about a little less than a half football field, let's say. So it's a very, very large room. But it's also it's also very clean. If you've ever been to these ginormous mega data centers of modern clouds, you may see something very similar. But what you see different is the machine is extremely clean. It's probably the cleanest large-scale data center room in the world. No cardboard boxes or wires hanging around, stuff like that. It's extremely it's pristine and clean, and I'd like to keep it that way. My room is not, but I'd like to keep my computer room clean. Okay, so like I said, there are 160,000 of these, and it's connected by advanced networking. And as advanced as the processor is, it has 48 cores, or actually has 52 cores per socket, 52 high-performance ARM cores per socket. It also it's the first 7-nanometer server processor on the market. Other vendors might claim otherwise, but it's a fact. This chip was fabricated first in 2018, so it's the first 7-nanometer server processor. That's not only being the chip CPU cores, but also it incorporates two key innovations. One is it incorporates high bandwidth memory, HBM2, on the same package in the same manner as a GPU. So that's to realize extreme high bandwidth. So even today, H2FX has the highest bandwidth per flop or per package of any chip in the world, 1 terabyte per second. Any general purpose CPU in the world, that is. So it's basically as a memory systems is comparable to a GPU. GPUs have HBM2, so it has like 1.5 terabyte per second memory bandwidth, but it's the same with H2FX. So things that run very well on GPUs also run very well on in relevance to general purpose CPUs, run very well on H2FX as well. So that's the chip, and that's a die. You see, that's a show card. So it's not, you don't get a smart card with H2FX. I'm sorry. But in the center, that's the silicon, about 500 square millimeters. And the package is large because just like the GPU with the HBM2 package, it incorporates the 4 HBMs on the side. Now, a lot of 500 square millimeters not only hosts the 48 cores, but also hosts the network switches and those network interface and network switches on the same die. So if you look at Fugaku, you see the racks. And if you come and see, people may wonder, where are the network switches? Well, there are 160,000 network switches because the network switches are all embedded in the die, just like BlueGene-Q. So one may argue whether BlueGene-Q processor or which is for predates Fugaku, or the A2FX would be the first chip to incorporate network switches on the same die. But if you consider some general purpose processor to run something like Windows, then A2FX obviously is the first in the world to incorporate the switches. In fact, because of this, that's how it allows scaling to 160,000 nodes, switchless, well, glueless. So all you have to do is hook them up using an optical fiber network, and you get 400 gigabit per second injection bandwidth per chip per node, not per multiple chips in the node, but one per chip, 400 gigabits. So the collective bandwidth out of the network, out of the entire machine, is about 5 petabytes per second, which is 10 times greater than all the data centers, including Amazon's, Microsoft's, and so forth, in the world combined. And that's according to Cisco. So it's not our data, it's Cisco's data. So we got a machine with quite a fast network. So if you look at the board, it has 2 chips, but this is 2 nodes. It's a 2-node package. This is a water-cooled package. There's also, Fujitsu has also built a air-cooled package, which is a little bit less dense than this one, but since it's water-cooled, it's a lot denser because there are 384 nodes per rack, or about a petaflop per rack. And you see it's water-cooled, and you see 3 differences between this and a standard PCB on your normal cluster. One is, of course, water-cooled, so you got all these heat pipes and water jackets and heat pipes. The second is you got these connectors which connects directly to AOC, so there's no hassle with the external NICs or anything. There's the direct optical connection between the nodes when they're a little bit farther apart. There are 100,000 AOCs in Fugaku, but because of 60 torus, each cable is not that long; it's about 20 meters long. But when you have 100,000 of them, the cable length is about 2,000 kilometers. Not as much as SKA, but it's in a single route. So the total, also you don't see any DRAM sockets. So because of HBM2, all the DRAM is embedded in the package. So here you see the fiber, and you see all the nodes. There are 96 on each side, and it's the double-sided rack. And there are 192, and 384 in total. So, by the way, you'll see me speaking. If we had audio, you'll see me speaking, but I guess it's a lot better because it's been dubbed. I'm speaking Japanese, and it's being dubbed, so it's probably better for me to speak in person. But see me speaking, which means that this room is actually kind of fairly quiet, and that's because it's water cooled. So at maximum, this machine can consume up to 35 megawatts. Although in normal operation, it's about 18 to 19 megawatts. So when you have something like 35 megawatts operating air-cooled, there's just no way you can even make a speech or even survive your eardrums to survive without protective earpieces or even like headphones. But it's very quiet because it's the machine is over 90% water-cooled as a result. So yeah, so that's the Fugaku tour, and when the COVID is over, I would very much like people to come and actually see the machine physically, because as much as we can describe stuff on video, you can't really sense the magnitude of the scale of the machine unless you're there in person. So I already talked about some of these things. It has CPU with highest, with high performance, high bandwidth, while being ARM, standards compliant ARM processor. Of course, the internal microarchitecture is our own, Fujitsu's, but it's compliant. It's compatible with standard ARM on your cell phone. Has switches, 160,000 switches, 160,000 nodes, as I described. And also, it's a disaggregated architecture in that the processor, the memory, and the network all can operate independently. And this is done to minimize the latency of a MPI communication. So the end-to-end latency, lowest latency achievable is about 0.5 microseconds, instead of being like 10 50 microseconds on Ethernet, which is about 100 times slower. So Fugaku was not only Fugaku is considered fastest, not because it's fastest on the top 500, but also fastest in all the other benchmarks, which are more important, like HPCG, which is conjugate sparse linear algebra, conjugate gradient, HPLAI, which is a proxy to deep learning convolution network, and also the Graph 500, which is a big data benchmark. So we supersede the number 2 machines by several factors in most benchmarks, and even in AI, we excel over very large GPU machines like Oak Ridge Summit. And but of course, the intent of Fugaku was not to excel in the benchmarks. Of course, the cost performance of Fugaku is really excellent. Had we built it out of off-the-shelf processors, it would have cost 3 times as much. But still, it's very expensive. So the real objective was to have breakthrough results in sustainable applications for societal sustainable applications like health and medicine, environmental disaster, energy, materials, manufacturing, and of course, to some extent, basic sciences. That's because it's also important in Japan too. So the objective was to achieve 2 orders of magnitude, nearly 2 orders of magnitude speed up over its predecessor K computer. And as you see on the chart, you see the areas in the applications. And you'll see that for these target applications, we have achieved largely achieved the target goal of about 70 on the average, and some applications more than 2 orders of magnitude faster. And of course, the software stack has been very general. You got the traditional HPC software stack, and then of course, but it's running standard enterprise Linux unmodified. It's Red Hat Linux unmodified. It's ARM, ARM distribution. So all the traditional cloud stuff, like the EC2, all the EC2 as if it were EC2, also run out of the box. So the only thing that required significant implementation challenge was the deep learning software stack. And I don't have time to go into detail why that's so. But actually, it's a implementation challenge for any type of processors, not just of course x4FX, but for GPUs, anything. So if you have a very fast AI processor, consider it's not the hardware, but it's really the software. It's not only hardware, but the software pieces that really excel. Anyhow, we got the combinations of AI and HPC, AI, and big data all encapsulated and coexisting on the same software stack, the Fugaku. And this is really the artifact, the result of Fugaku, not just the hardware, but coming up with this converged software stack, such that the user can run anything of any combination on very fast on a uniform way on this very massive machine. Is one of the most important artifacts. So one idea is to make the software stack open and available to be run on other infrastructures that facilitate its ARM SVE compatible processors, like the upcoming Graviton 3. But we'll see. But we're working on. Let's try to work on that. So despite the size, Fugaku is very successful in getting users. Machine is pretty much full right now. We're about almost a year into production, and well, this was August, but this since we came full, we continue being full basically. The power consumption is not too bad. So we're not that much greater than the K computer because the machine uses a little bit more power, but because we have more efficient cooling, overall the total power consumption of the site is about 20 megawatts or so, which is way below our goal actually, because the facility was designed to host up to about 38 megawatts. I'm sorry, 42 megawatts. And of course, if you run some power-hungry applications, which turns out to be HPCG, you can go up to 35 megawatts, but on the average, it's about, constantly, it's about less than 20 for the machine. So, if you consider Fugaku to be an exascale machine, we have largely satisfied the US DOE goal of achieving exascale performance with 20 megawatt power restriction in production by 2020. So that's so basically satisfied the goal for them. The Fugaku, as Tinwi mentioned, is being made available internationally, actually. So anybody in the world can apply. But also for Singapore, we have a Singapore Inclusive Allocation Program. In fact, our sister organization, RIST, which does the allocation, instituted a program with the NSCC to do so. And so there are applications from exclusive to Singapore. And also a similar thing is being worked on with A-Star ACRC or RSC and HPC users. And that's being tested. That's undergoing tests right now. And how many minutes do I have? Lost the track of time. Yeah, so just a few highlights on the COVID now because I'm running out of time, I think. So Fugaku, even from pre-production, when Fugaku was being installed just in February of 2020, that's when COVID hit. And it was quickly realized that the Fugaku would be deployed for COVID usage. So we quickly stood up a program with our ministry to host. So there were, many efforts also going on at our tier 2 centers. But for Fugaku, we really wanted to focus on applications that would require the immense power of Fugaku. So the stuff that could not be run on our existing machines, which are of, let's say, several petaflop to tens of petaflop performance. Because it will dominate the entire machine. If you kick the other users out, maybe you can, but you can't do that. So 6 projects were awarded from a very molecular studies, first principle studies of COVID. For example, what the bonding strength was, depending on the strains. The new strains, of course, has stronger bonding, and this was so exact mechanism that was investigated. Transpositional drug usage. But these types of micromolecular studies are also done in other supercomputers, but this was done at much bigger capacity, enough capacity to fill the entire 10 petascale, multi-10 petascale supercomputer for the entire year. But also, as Tsubokura-san had presented briefly, more societal epidemiological studies were also done at Fugaku, including droplet aerosol infection simulation, and also societal simulations of like when, what would happen when, what are the economic implications when there would be a lockdown, by analyzing entire Japanese transactions between all the companies in Japan. So also this aerosol simulation would require, as Fugaku-san said, about 50 digital twins of a variety of societal situations were created, and about over the 1,000 cases. And this again would require the entire dedication of multi-10 petaflop scale supercomputer for over the course of a year. So with that, we received the Gordon Bell Prize, one of the Gordon Bell Prizes awarded this year for COVID, and this was for COVID. And we're very proud and very happy that we've been able to contribute to the world and also be recognized as so. And I won't go into details since the lack of time, but again, just to repeat, that we were able to do all these COVID applications, and in fact, not just one that Supercomputing mentioned, but also most of these COVID applications that you see are basically translational from the SDG applications that were already in flight and optimized for Fugaku. So for this translation was from the engine combustion injector research into into COVID aerosol research. But similar translations were done for molecular studies, for first principle studies, and economic studies, and so on. So it was somewhat, well, I wouldn't say fortunate because I think the word is inappropriate, but in some sense, it was, I think we basically were able to deploy Fugaku very quickly, even in pre-production to COVID, because of our readiness. And I think that permeates to all other machines. One of the reasons we conduct these advanced research on any supercomputer in the world of any sort of size and scale and generality is the very quick repurposing of the research and the applications and the machine to respond to these crises. And the aerosol one, all the molecular studies and so forth. But very quick, let's say, call to arms of how we can respond is one of the most important properties of one of the most important missions that we have experienced with this COVID-19 pandemic experience so far today. So I'd like to end my so this was carried to many 350 TV stations, in fact more, as we see more every day, and over 1,000 newspapers and web news and so forth, and was incorporated into the public policy. And interest of time, I'd like to skip all these, and just to come to the final conclusion that I'm sorry. Ooh, okay. Final conclusion that we are, and so basically Fugaku is here today, and we're contributing to society, and we welcome users from Asia, and including, of course, Australia, our friends Australia, and of course, we'd like to partner with these institutions, and we are partnering these institutions, NSCC, NCI, so forth, and ThaiSC, so forth. And finally, we are getting ready, but we're starting our endeavor for the next one. Now, it remains to be seen if we can build something that's 2 orders of magnitude faster than Fugaku, but it looks very promising. So stay tuned for 2029. Thanks very much.
Thank you kindly, Professor. All right, ladies and gentlemen, we are going to take a very, very short break, and thereafter we will reconvene at 3:50. Time check right now is just 3:44. In about 6 minutes from now, we'll reconvene, and of course, we'll then move on to our next speaker, Dr. Piyawud Srichakul. He will come on at 3:50. Thank you.